do have to, I should have the recorded video on the website. Okay. Continuity. The basic rule of thumb, but don't you dare ever write this on your AP test. Shame. Basic rule of thumb is you take your pencil and follow the line and never have to lift up your pencil, right? Follow the curve. It's continuous. You never have to lift up your pencil, right? But shame, never ever write it on your AP test. You have to use the definition of continuity. That's what we're talking about today. But I mean, visually with your eye, you can see, could I actually move my pencil along and never have to lift up my pencil? But on the AP test, you cannot say that, or they will give you 0 points. You have to use the definition of continuity. So, f(x) is continuous. At C, this ISF, if and only if. So we're going to read this definition both ways, and both ways are still true. If you're going to read the ending towards the beginning or the beginning towards the ending of the definition, both ways are true. If and only if 3 things must occur. F of C exists. F of C exists. Okay? So, if we have an S occurred, let's see, F of C would be the y value of that point, right? F of C. So as long as that exists on the right track, the second thing must occur. The limit as x approaches C of f of x also has to exist. So remember, for the limit to exist from both the left and the right, we have to go to the same height, right? Yes or no? The left and the right have to be approaching the same point. Okay? So now the limit, that's going to be a hole at that point. But for continuity, we must have that filtered hole, right? Because it has to exist at that point. And we have to come in from the left and the right, and be at the same height. Okay, and lastly, both that point, F of C, must equal the limit. Hi? Sure, everyone looks studious and pretty at the same time. Okay, so here's an example of F of C existing. Oops, excuse me, I need for this. Here is C. F of C exists, true? I didn't write it all. Does F of C exist? At C, we have floating point over that spot, right? Does the limit exist at C as x approaches C? From the left and from the right, does the limit exist? When approaching the same hole, you can't, it's either yes or no, but it's not a maybe. It's approaching the same hole from the left and the right, correct? But is that hole the same as equal to that point? No. So this is an example of where part 3 fails. F of C exists, and so that exists, but they're not the same. So this should be not continuous. Does that make sense? Has to pass all 3. Okay. So we have a little function. This is actually the same one that's on your pink sheet of does not exist, undefined. It's really small though. Let's see if we can make it even bigger. Okay. So we're going to go through a few things to decide if it's continuous. So first of all, go ahead. I don't know how to get to it. Okay. Is this function continuous? No, you can just visually see, right? If I just draw this and have to pick up my pencil a lot of times, right? So you never ever see that on our AP test. We have to use the definition and prove that all three of these work or which one fails. So we're going to go through the next first, all the points of just continuity. Where's the first fail? Starting on the left. Where's the first fail? At -2. Right, because we have a jump. Okay? Where's the next fail? Yeah. -1 first, will it be? There's a hole there. You can probably see it better on your page. Uh-huh. No. Because you could have a starting point, and the square root function has a starting point that continues forever. Okay, so we have -1, +1, what's the next one? 3. 2, I think, is fine because we have a fill-in hole array. Yeah, okay, so we're going to go through each of these and say why in definition terms. I'll just because I can pick up my pencil and have to start again. Oh, yeah. Yep, we can use 5 too, we have a hole. Yeah. Okay, so why are they discontinuous at x equals -2? Let's see, say what it fails. So at x equals -2, does f of c exist? Does f of -2 exist? And therefore the point at -2. Yes, so that one passes. Look at part 2, the limit as x approaching -2 exists. From the left and the right, are we approaching the same point? No, from the left we're approaching 1, from the right we're approaching 2. So if I will come from the right, I'm approaching 2. So that's what it fails. So the limit as x approaches -2 of f of x, good job, on paper, right, does not exist. Okay? Okay? What about at x equals -1? Does f of c exist at -1? No, it fails the first one. So this is how we write it in technical terms. Limit as x approaches -1 of f of x, you can't not have the f of x. They have a hole, so it does not exist. That's the one that fails. It passes the limit though, is the limit on the left and the right the same? Yeah. But if it fails 1 or 2, then it automatically fails number 3. Okay? So, with your neighbors, I want you to go through all of them, see if you can come up with a mathematical definition statement for the reason why we fail at 1, the reason why we fail at 3, and the reason why we fail at 5. She's totally right. The limit exists, and I wrote the wrong one. On negative 1, the limit does exist, but it's the f of negative 1 does not exist. Because the limit from the left and the right does work. X approaches, there you go, I erased that. Sorry, so yeah, that one failed, number 1, negative 1. The number 1 off of the list. Okay, so Jasmine, what did you put at x equals 1? Mm-hmm. Why does it fail? And what? Okay, but does f of c exist at 1? Yes, it does exist because we have a filling hole. Does it exist from the left and the right? Are we approaching the same point? Yeah, we're approaching the height of 2, right? 1 comma 2. But is f of c the same value of f of 2? No. So in this case, 1 does not equal 2. So we would say it doesn't exist because f of 1 doesn't equal the limit as x approaches 1 of f of x. They're not equal to each other. Okay, what do you think about x equaling 3? So just go down the list. Does f of c exist? Does f of 3 exist? No, right? Because it goes in threes, it gets closer and closer to x equals 3, but never actually touches. So f of 3 does not exist, right? And even fails the second one, doesn't it? Does the limit as x approaches 3 exist? On the left, where's the limit going? Infinity. On the right, where's the limit going? Negative infinity. So the limit doesn't even see this. So it tells both of those. Okay, and 5. Does f of c exist? Does f of 5 exist? No. Okay, so f of 5 does not exist. Okay, is that clear? Now, knowing those points of discontinuity, I want you to try to create the domain of this. It starts on the closed point and open point. There's a long parameter left and right. But the domain, knowing the points of discontinuity. Writing the domain. The inner for the domain of this discontinuous function. The domain's actually up here. Yeah, the domain's above that whole list we just did. Sorry, it wasn't very clear. Ooh. Okay. So horizontal spread is the domain. Teams of x from smallest to largest, you always do range and domain. Domain is horizontal spread. So what's the smallest x that this graph incorporates? -3, it should have to be a parenthesis or bracket. Bracket. -3, comma. Now this one, -2 has a point, right? How could -2 exist? How could -1, does that exist? No. So the -1 parenthesis union, let me start again. -1 until what's the first part of the domain that doesn't have infinity? Then all this graph is also going up. Is that what the domain is? It's going up. No, it goes until the x value 3. So you should have infinity yet. Start -1 until 3. Those are all parentheses because we either have an open circle or we have a red glass material. The last section is going down to anything, but that's not what we're looking at. The x value is approaching is what? 3, and then it gets closer and closer to 5. So, but we have a whole lot 5, so we have 3, comma 5. All the way up to -3, the only one with a bracket. Any questions about the domain? Okay, make this smaller now that we don't need to look at the graph. Okay, the domain of a function. To find the domain of the function, to find the domain of the function, we look at the points of continuity. To find the domain of the function, we're listing just the points it's continuous. Okay? And where it's continuous, we find the domain. Now, there are some points along the graph where it wasn't continuous, but the x was still represented, right? By the whole above or the point above. So might not necessarily have been continuous at x equals 1, but x equals 1 had a value, right? 1 comma 1. Okay, so we have a couple different types of points. We have non-continuous points that we need to pay attention to, and we'll also have continuous points. And these continuous points are also differential points, which we'll learn about later. Does that sound like something you've heard of in calculus before? Differential points. So we'll learn about what differential points are later. Not today. Okay, so we've already found there are 3 types of discontinuities. We've already found them on this graph. Where do we have discontinuities? Let's just the things we see the graph that created discontinuity. A bird glass hotel, jump, and a hole. That's it. The 3 things that create our discontinuities, we have a hole. Like this, right? So a function is that we have a hole in the middle. We can have a jump. So maybe it's like a piecewise function. It starts linear, and then it goes like quadratic, something like that. And then the asymptotes are an infinite discontinuity. It's going to infinity. Infinite discontinuity. Okay, so if we have like an asymptote, maybe we went up here, and this doesn't really matter. There. So Okay, so the three-pronged tempo, we're going to identify what's the discontinuity that's represented on number 1, number 2, and number 3. We briefly talked about these at the very beginning of class. So we're going to try to decide, once you're entering those functions, what type of discontinuity is it? Is it a whole? Is it an asymptote? That's an infinite discontinuity, or is it a jump discontinuity? Okay, turn to your partner. Work it out. What makes it a whole? We talked about this at the beginning of class. What makes it an infinite discontinuity? We also talked about that at the beginning of class. I disagree with the first method. Yeah. Yeah. Is it good? I really like that book. I watched, what's that movie? It's a movie where, like, the Earth is dying or something, so they send, like, buoys up to some, like, training center in space. Endgame. Yeah, I watched that and I was like, this movie is so stupid. But the whole time I was like, all this is Lord of the Flies. Because they, like, how to build teams and survival. Yeah, and it is. I know it's a book, but I was just like, that's all it is. It's Lord of the Flies. Okay, number 1. What type of discontinuity? Why? Is it called an index function? Things like with R. No, rational. The parent function is f of x equals 1 over x fraction rational. But yes, you have a shift. Opposite, inside, same, outside. So our 1, 2, 3, we have our asymptotes shifted over. But this is a non-removable discontinuity, right? This is consolidating in the numerator. So non-removable, removable is a vertical asymptote, so it's our infinite discontinuity. Okay? But that's number 2. At what point? At 3. Good. So we have a removable, which creates a whole at x equals 3. So I will hold over it again. It is a whole discontinuity. And the last one, f of x equals 2. What does that function look like? Will equal a constant. No, will equal a constant. What does the graph look like? Okay, I'm going to ask this. I think you know someone like can show me what they're on correctly. I don't know if it's like, I don't know. Or you're just too quiet. And the equal a constant is that horizontal line. So at x equals negative 1, let's see, x is less than negative 1. We're at 2. And greater than negative 1. We're at 3, but not inclusive of 1. So what type is that? Jump. Okay? Jump discontinuity. Any questions? Mostly have that. Okay, flip it over. Determine whether the function is continuous and discontinuous. Oh, where, not if. Determine where the function is continuous and where discontinuous. Okay, so we're looking for those discontinuities. Maybe it's a hole, maybe it's a jump, etc. So let me try number 4 with your neighbors. 1, 0. Yeah, on the back side of this, it's re-recorded so you can watch the video. Put it on Canvas. Number 4, determine where it is continuous and where it is discontinuous, if at all. This is just kind of the key to know the difference between non-existent, undefined, and indeterminate. But, no, this is just for you to keep in your folder to know. And this will be on Canvas, the video will be. We took a quiz at the beginning. Oops. Okay, Christine, what do you think? Okay, because we have, it's not removable, right? Okay, so we have a non-removable, which creates, what is it if it's not removable? Vertical asymptote at x equals -1. So if we were to write the interval of continuity, or, where it's continuous, what would that interval be? Yeah? What would I put on -1? Okay. Good. Does that make sense? Covers everything except for -1. Okay? What about number 5? Square root function. And the square root function is regular domain. The parent function is go from the infinity to positive infinity. No. So you have to understand how the shifting works. And where it is not, where it doesn't exist, where we don't have a domain, right? And where the domain does exist. And is there anywhere this graph is discontinuous? Is there anywhere this graph is discontinuous? Good, like a division by 0 problem? No, this is -2 due to the square root function. Horizontal shift, right, 2, right? So our graph, be 1, 2, starts at 2, go like that. Yeah? So where is it continuous? What's the interval which is continuous? Bracket 2 to infinity. Yeah? Because we actually have a physical plant. If you plug in 2, you get square root of 0. If you plug in anything smaller than 2, though, you get an imaginary number, right? Okay, so number 6 is not a square root function. Try that one. Remember, square roots. This matter numbers if the square root is negative, right? So the square root has to be 0 or larger. It can be discontinuous, but it's still an interval being continuous. That's where it starts. So it starts with 2 and then goes to infinity. for square roots, what's the smallest number we can take the square root of? 0. Oh, you're on the right track. Yep. Yeah, good. Mm-hmm. So, if you're completely lost, we cannot take a square root of 19 smaller than 0. So, the question with 5 minus 3x to find what's the smallest value I can plug in to keep this 0 or positive. It's not a great number. Yeah, but how do you get factors? Okay. So how did you find factors? It's not hard to explain. You just set it equal to 0. Set the radicand equal to 0. And so, because we know it can be equal to 0 or larger, but it can be smaller. So when you solve, you get x equals 5/3. Now the question is, x equals 5/3. Does the square root go this way or does it go this way? How do I know that it goes left? Because the x is negative. Or you can just take all values and look at what happens. Is it going left or is it going right? Okay? But the x is negative, so then we have to work on the flip. So it's not this one. Okay? So, Kennedy, what would our continuous domain be? Parentheses. Bracket. Good. Okay. 2 more. Try number 7 and 8. You have to know, this is why we went over all of the different parent functions at the beginning of the year. You have to know what these parent functions are, and what all the shifts are, and what all the flips are. There's vertical flips and there's horizontal flips. If you think you have solved number 8, let me know. I think number 8 is going to test you a little bit if you really understand what all the shiftings and transformations are. Now I'm checking, you think you know what number 8 is. Because he wants to know that this is long. I've never said long, like, as a habit. I've always said natural long. I never actually never said long. Someone else said, like, written. Other people say written. Yeah, I just say natural long. Yeah, let's do 7 and 8. 7 should be easy. Just look at what function it is. The shifting doesn't matter on number 7. I know that. Not what you wrote was the range. 7 sounds more. Good. No, this one's more tricky than you think it is. Think of what the parent function natural log looks like. And then think about what that inside the parentheses does to the function. Good job. Okay, let's look at number 7. What can be functions number 7? Parabola. What is the plus 5 due to the function? Vertical shift of 5. So we're up here at 5, and it's an upward concave parabola. What's the domain? And is it continuous everywhere? Yeah, so we have a continuous domain. Domain infinity to positive infinity. No, what are you talking about? Okay, number 8 though. What's the current function of number 8? Natural log of x. What does the natural log function look like? What's the natural log function? Natural log be negative? No, I don't think that's ready. Now, we have some shifting. This is negative. The x, which tells you what type of flip is it. Horizontal flip. So I'm going to do some manipulation here so I can see my flip. I'm going to factor out the negative. So I have negative x minus 1. Will that work? Distribute back in. So I can see both my horizontal flip and what's that minus 1? Horizontal shift. Which direction? Right, because it's the opposite of what's inside the function. Right 1. So we have a horizontal shift right 1. So our asymptote is going to be shifted horizontally. So it's at 1. Instead of growing to the right, we have a horizontal flip. So it's going to go this way, right? Okay, what's the domain? Page 1, should we have a bracket? No, because we have an asymptote we're getting closer and closer to. Now all of these are continuous functions within their domain, right? Continuous function is continuous for every part of its domain. Inside the domain, none of them have holes, or it's actually a separate one. This one, right? This guy is every one. He wasn't perfectly continuous. Number 4. Okay. The very last part of this is something very important. There are 3 theorems this year that all have abbreviations. So we got abbreviations that can be confusing. IVT, MVT, EVT. So those are IVT. If you could drop these by name, it was incorrectly on your test. So definitely scoring points. IVT, intermediate value theorem. Yes? You can just say IVT. They know what that is. Intermediate, you do a lot of explanations. Prove how you know this. And with continuity, you can't prove it and say because I can follow with my pencil and never with my pencil off. Shame. These are 3 rules for a definition of continuity, right? You can prove that all 3 of those hold. And you prove using IVT, you did just say by IVT, and then it works. So what is IVT? A function f of x is continuous on a closed interval. A to b takes on every value between f of a and f of b. So let's see this as a graph to help us understand a little bit more what I just said. We have to have a continuous function. So is that continuous? Yeah. Here is a, here is b. Continuous between a and b? Okay, from a closed interval, I'm going to put brackets right there. Closed interval is important. It's continuous on a closed interval from A to B. Now, here is f of a, right? The height of that point is called f of a. And the height of this point is called f of b, correct? So the intermediate value theorem says if our function is continuous from this interval, from closed interval A to B, then every point in between takes on every value between f of a and f of b. Meaning every point in between must take on every height in between f of a and f of b. All of these values must be represented. Because they could, here's a problem. Explain why the function has a 0. On the closed interval, 1 to 2. So this is how you do it. You plug in 1, f of 1, using good notation, and put f of 1, a2 plus 3 root 1 minus 1. Parentheses in physics considered actually means grouping. Is there anything here that's grouping that's not necessarily parentheses? The square root, so that's actually in the parentheses family because it means grouping. So 1 minus 1 means 0. We multiply before we add. So we get f of 1 is negative 2. Do it again with the other endpoint of our interval, f of 2. If we plug in f of 2, 2 minus 1, we do the grouping product, which is a square root. You multiply by the square root of 1, is it just 1? So negative 2 plus 3, we get f of 2 equals 1. So the question is, why does the function have to have a 0? So f of 1 is way down here at negative 2. F of 2 is way up here at 1. Because this is a closed interval and it's continuous, that means every point in between has to be represented at least once. So I'm going to have to cross the x-axis at least once to go from here to here. Yes. So that would be my answer. Here would be a great way to write it. Oops. Let me go on the other paper. Here would be a great way to write it, which would look beautiful on your test. After that is continuous. So this works, it has to be continuous. So you want to drop the continuous word. On the closed interval, it has to be closed interval. Closed interval, 1 to 2. And it's proven f of 1 equals negative 2. And f of 2 equals 1. So we proved that we did some work. We found a number below the x-axis and a number above the x-axis. By the intermediate value theorem, there exists at least one value. There could be more. By the IVT, there exists at least one value such that f of x equals 0. That would like the golden point on your AP exam. Okay, so 2 and 3 is the homework that is with continuity. Okay, lots of questions on that next time. Would you take 2-1 and 2-2 and check in your folder before you leave? And please stay for 2 minutes and get that quiz. Did you finish your quiz? Good. The other day, one or two guys that didn't finish their quiz. The question is, I put them on the table. The question is right there. It was not two guys. It was Maddie and someone who didn't know me. Was it you? Okay. Did you finish your quiz? I'm just going to correct this. Yeah, I think we just need to correct it. Any minors? Picture 2-1 and 2-2 is in your folder. We escape by staplers in the front and in the back.